a quick introduction to Jules, right? Oh, you're ready already. That's great. Okay, so Jules, as the next speaker, right? He's actually a hobbyist. That's really cool, right? He's been doing his own stuff, extremely interested in mathematics, cybersecurity, and programming languages, of course. In fact, he's part of this very prestigious group called the Social Engineering Experts. And in case you don't know what that is, it is actually Singapore's top, I say that again, is top #1 competitive team. In fact, he has ranked globally 27 as of just recently, September 2022. That's amazing, right? One of the 2 members who specialize in cryptography. Right, this talk is not about crypto like the Web3, right? It's about writing your own cryptography, so that's going to be exciting. So this talk, right, if I may just give you a quick introduction, right, in case you might have heard about 2019, there was a flaw in Flickr that allowed user kind of impersonation. So this is one of those things that, where we think about cryptography can be very fragile. And without stealing Jules' thunder, we're going to hand the time over to him to tell us more. Why don't you give him a round of applause, please?
Okay, so today I'll be talking about like cryptography, but specifically I'll be talking about like applied cryptography. So this talk will sort of be like a summary of like applied cryptography, as best as I can. For those who are not familiar with cryptography, don't worry, I try to make the talk as like self-contained as possible. And all the examples I've given have like pretty much no math inside. So a quick overview of who am I. I have like 2 years of security experience where I did mostly reverse engineering and software development. And I played like cybersecurity competitions like what you said. But disclaimer is that I'm not a professional cryptographer. I'm not qualified. So I cannot do like certain tasks, like I cannot audit cryptography code and I cannot like design protocols and stuff. So for those who really don't know anything about cryptography, basically cryptography is about like managing access to data. Like you want to prevent some people from accessing a certain data, and also you might want to say verify the source of the data, like verify the integrity of the data. So an example of this is like HTTPS. If you access like a website, and chances are you will use HTTPS to like serve the website to you, which is it's a protocol that guarantees 2 things. It guarantees privacy. In other words, like the traffic that you send to the server and come and return is like encrypted, and also it guarantees integrity. So it guarantees that the message when it sends across the network is not tampered with, and also it ensures that like that it kind of like ensures that the website, the content is being served by the correct website through the certificate authority. Yeah, so with that out of the way, I'm going to give a short preview into like analyzing a very simple cryptography protocol. We'll be going through a protocol that's written by this company called WarpConduit. So this protocol was published in 2013, and I retrieved it from their website in 2022, which means they have 9 years to fix any issues about this protocol. So basically, this protocol does symmetric message encryption. So what that means is that you have like some plain text that you want to encrypt. So you have a key. You use the key to encrypt the plain text into some ciphertext. And if you want to decrypt it, you use the exact same key to decrypt. And this protocol claims to have another guarantee, is that it's able to detect whether a ciphertext has been tampered with. So if the ciphertext has been tampered with by an attacker that doesn't know the key, they claim that the protocol will be able to detect that and refuse to return the plain text. Yeah, so how it works is actually very simple. So you have some plain text. The first thing you do is to compute something called the MAC. You can think of it as like a checksum. And the important thing is that in order to compute the MAC, you need to know the key, which means that if you're an attacker that doesn't know the key, you won't be able to compute the MAC. So what you do is that you take the plain text, you append it with the MAC, and then you put it through an encryption algorithm. For this case, they use Virginal CBC, and you get some ciphertext and you just return the ciphertext. And then the decryption is pretty much the exact same thing, but you do it in reverse. The reason why you are able to do it in reverse is because if you have the key, you can reverse each of the operations. And then when you decrypt, you have an additional check. You check the 2 MAC values. And what I mean by that is that, remember how I said the ciphertext contains the MAC? So when you pass it through a decryption algorithm, you get like the MAC value, which is the orange box, it comes with the ciphertext. And what you do is that you take you recompute the MAC to get the green color box, and then you compare whether they are equal. The idea is that because if the attacker were to modify the ciphertext, they are unable to compute the new MAC value, which means that once you put it through the algorithm, it would be able to, chances are the two MAC values will not be equal. And so if the server checks the thing is not equal, chances are the ciphertext has been tampered with. So before we go into like actually analyzing the protocol, I want to introduce this idea called reasoning by Lego, which is coined by this cryptographer called Taylor Hornby. And the idea is like, let's say you have something that is made up of like secure, smaller parts that are secure, right? So if you put them together, the protocol should be secure. So to be more specific, right? Let's say this protocol has two guarantees. It has privacy and it has integrity. It guarantees privacy. In other words, like you cannot decrypt the plain text. You cannot decrypt the ciphertext without a key. And region 256 is a primitive that ensures that and is secure, so no problem. Integrity is guaranteed by the HMAC, which is underlying is like SHA-256, so it's also secure, so no problem. So this way of reasoning about a protocol, right, is very good for implementation, because you think about it, like you can abstract out like certain properties of it, and then you just have to combine them together. But it is wrong when you want to do cryptanalysis, because when you do cryptanalysis, you need to consider the entire system altogether. So the main flaw in this thing, right, is that the MAC comparison over here is not constant time. Yeah, I'll just gloss over the term now. I'll explain what the term means later. But what we'll see later on, right, is that with this like flaw, right, there are certain circumstances where you are able to recover the plain text without knowing the key. So if you still go by the reasoning by Lego, right, you would think like, okay, so the vulnerability over here relies on the MAC comparison. The vulnerability involves the MAC comparison. So if you think about it, if you like still reason by Lego, you would like be confused as to why it even affects the plain text, because like maybe if the MAC comparison is flawed, it might affect integrity, but it shouldn't affect privacy. Yeah, but as you see later, that's wrong lah. So I glossed over the meaning of constant time, right? So I'll explain what constant time means. Constant time basically means, right, that like if a function is constant time, it means that regardless of the input, right, the function will take the exact same amount of time to return. So here's a string compare that is not that is implemented in such a way that it's not constant time. So for instance, imagine in your code, right, you are comparing two strings. One is a secret and one is controlled by the attacker. And in the glibc source code that implemented string compare, it might compare character by character. And so let's say the attacker got 0 characters correct. It wouldn't even enter the loop, and it would just return immediately. Whereas if the attacker got maybe 5 characters correct, it would enter the loop and loop 5 times before returning. And that would take a slightly longer period of time. So the idea is that the attacker can return the secret if they are able to measure that time difference. So for instance, like the attacker can brute force the first character, see which invocation takes the most amount of time, and that must be the first character. Then they can slowly recover character by character of the secret. So the reason why cryptographers care about timing attacks is because there are certain circumstances whereby timing attacks are relevant as an attack. Because let's say like the protocol is implemented within like hardware, and the attacker is able to like have physical access to the hardware and probe the random stuff. Then they can measure the kind of time latency. And also like about 7 years ago, there was a paper that was released that managed to measure time differences across the network of the order of like a few hundred of a nanosecond. So this is when timing attack becomes like pretty relevant. A short aside though is that timing attacks are not always relevant. So you take a look at like the glibc source code for string compare on x86-64. As you can see here, right, it compares 32 bytes at once, which means that if you want to have like, if you want the code to loop once, you need to guess 32 bytes correct. And if you were to like count how many possibilities that is like 2 to the power of 256 possibilities, which is not feasible to brute force. But of course, like there are certain circumstances where it's still relevant. So maybe if like, you can control the alignment of the secret with the block, with the 32-byte blocks, then you could potentially use the timing attack. And also, unfortunately, before I go into the attack, I still need to explain like what CBC means. So CBC is a block ciphering mode, and the reason why that is you need a block ciphering. Okay, so wait, Regional 256, right? That this protocol uses, right, encrypts in blocks of 32 bytes. So Regional 256 alone can guarantee the privacy property in 32 bytes. If your message is 32 bytes, then it can guarantee that. Unfortunately, most messages that you encrypt is more than 32 bytes. So if you want to guarantee privacy across a longer message, you need to use encapsulation mode. So CBC is one such encapsulation mode, even though it's like probably one of the worst ones, which you'll see later. But basically, if you pair Regional 256 with like some block ciphering mode, you could encrypt larger messages. So CBC has like some very weird properties. I won't go into details, but yeah, it has some very weird properties. So first off, right, is that without the knowledge of the key, an attacker can truncate the plain text by 32 bytes. So for instance, like if the attacker is given a ciphertext that starts with like AAA, BBB, CCC, the attacker can, without knowledge of the key, modify the ciphertext in such a way that it decrypts into AAA, BBB, so there's no Cs. Another property of CBC is that the attacker can combine two ciphertexts together. So if the attacker has like two ciphertexts, and that one, the first one decrypts into AAA, and the second one decrypts into 1111, the attacker can put them together in such a way that it decrypts into AAA and then some random data and then 1111. Yeah, it is these like weird properties of CBC which will be relevant, which will end up affecting the plain text, even though the vulnerability is within the MAC. So I still need to explain like exactly under which circumstances this protocol is vulnerable. So here's the circumstances that I propose. Let's say the server implements the protocol and it can encrypt anything that the attacker sends, and it will return the ciphertext. Then the server can also decrypt whatever the attacker sends, but it doesn't return the plain text. So the goal of the attacker is to recover the secret given its ciphertext. And note that like if the protocol is actually secure, there's no way for the attacker to do this because the server doesn't return the plain text. And of course, we assume the attacker can exploit the timing attack. So I want to make the comment that this is not an obscure scenario. So a scenario that this could happen and is more common in the past is when there's some like maybe you access a website, you log in, and then the server sends a cookie over, a session cookie. So some servers, right, would put like some sort of server secret inside the cookie, and then encrypt the cookie and send it to you. And every time you make a request to the server, you send the cookie over, and the server will decrypt the cookie, pass the values inside, and return some results accordingly to like what the values in the cookie are. But the server will never return like the plain text version of the cookie. So now I can finally go into the attack lah. So the first thing the attacker should do, right, is to get 256 ciphertext of plain text that start with byte 00 to FF, and we'll name that ciphertext like A0 all the way to A255. So the attacker can do that by just simply requesting the server to encrypt their stuff. Then we put all these ciphertexts aside. So next thing the attacker can do is to take the first 32 bytes of an encrypted secret and prepend it with like some random block of 32 bytes, and then just send it to the server. So what this does, right, is that it tricks the server into thinking, because of the weird properties of CBC that I mentioned earlier, that the orange block over there, supposedly the HMAC, actually becomes the first 32 bytes of the secret, like unencrypted secret. And so the attacker can just try different R0 values, just try appending different random 32 bytes in such a way that the first byte of the orange block, which is the secret you want to recover, equals to the first byte of the green color block. And the attacker can tell when this happens through the timing attack. Then the attacker can okay, so at this point, right, we know that the first byte of the secret, right, is equal to the first byte of the green block, but we still don't know what the first byte of the green block is. So the attacker can then replace the first byte of the first 32 bytes of the secret with like the known ciphertext, like the A0, A1, A2, A3. So the idea is that, say the attacker tries A42, right? Then the first byte of the orange block will become 42. And if it matches the first byte of the green block, then you will have found the first byte of the secret. So this attack can be extended to recover the first few bytes of every 32-byte block in the plaintext. And if you are able to adjust the alignment of the secret value, right, you are able to pretty much recover the entire secret. So I hope y'all weren't too lost in that like very short primer of cryptanalysis. But it honestly, as long as y'all get like sort of a general gist of like how this can go, it's fine. You just need to take away like these two things. So first off is that different parts of the protocol can screw each other up. And also there's a lot of things to consider beyond the primitives, like beyond SHA-256, beyond like whatever primitives you use, is also about like how they interact with each other. So I keep on saying system, right? But like what exactly do I mean by system? I've been glossing over that. So there are many ways to formalize it. I'll be stealing a formalization that was done by Quark's Lab, which is a pretty cool company. So this is how they formalize cryptographic usage. And I won't cover like the entire right side of it because, left side. Yeah, my left side. Yeah, because it's, in my opinion, it's like quite context dependent, and it's closer to like vulnerability exploitation. And I'm here to talk about cryptography. So so in any cryptographic protocol, right, you need to first start with a hard mathematical problem. So for instance, RSA. I hope you all know what is RSA. It's basically an asymmetric encryption protocol that is that relies on the hard mathematical problem of integer factoring. In other words, it's like very hard to factor a large number that has large primes. Yeah, so through this hard mathematical problem, it can build primitives like RSA. And when it comes to implementing RSA, you need to start thinking about like what algorithms you need to implement that is in a way secure. So for instance, like you need to implement constant time operations so that the act of decrypting or encrypting something won't reveal anything about the key or the message. Then once you have like, okay, so and then once you have that, right, okay, for people who know like a bit more about RSA, they will know that like RSA itself is not secure. You need to wrap it up in like some form of encapsulation. So for instance, you need to implement padding over RSA, and so that this is like secure in itself. Then once you have like sort of like a kind of secure primitive, you can start to implement stuff, use it in like other places like in protocols and in crypto systems. So underlying this entire thing, right, is specifications like how should the primitives interact with each other, what parameters you should use, like what's the size of the primes and so forth. And there are also various considerations when you write a specification. Like for instance, like you need to think about what kind of hardware is going to be implemented on. So for instance, like AES, which is a symmetric encryption protocol, implementation has to be resistant to cache timing attacks, which is an attack that is specific to certain CPUs. So in the attack that I just covered, right, this is other stuff we considered. We consider the hardware because you need to see like whether the timing attack is even relevant. We also need to consider like the implementation, like is it implemented in PHP and so forth. And we attack the CBC mode, the CBC encapsulation. And also in order to figure out like why the protocol is vulnerable, we also need to formalize like exactly in what situation the protocol is vulnerable. Unfortunately, where most developers stop at is at the hard mathematical problem. They kind of know how RSA works, for instance, and also they know RSA exists as a primitive, and maybe they touch a little bit about modes and encapsulation. And at least now I'm in uni lah, so I noticed like unis when they teach like, for instance, like introduction to information security, and they cover a little bit about cryptography, this is pretty much where they stop. They don't talk about anything else for cryptography. So I think this characterizes like most vulnerabilities, even outside of cryptography, is that vulnerabilities are often characterized by like unknowns, stuff we don't know, the things that we don't know. And this is a big problem because if we were to know what we don't know, we can simply like ask the right questions. And that's the thing about implementing cryptography. You want to have an expert to implement the cryptography for you, because for a professional cryptographer, the amount of unknowns they have, right, is a lot smaller than a regular developer. So they are able to like design protocols and stuff that are less likely to have vulnerabilities. Yeah, so just for fun, I'll be going through one real-life attack. In the interest of time, I'll just go through one. So let's talk about Hyundai. So Hyundai has their car has this subsystem called the Audio 2V that occasionally receives firmware updates from Hyundai. And usually firmware updates have to be signed because the firmware itself has to know where they are getting the update from. They need to ensure the update comes from a trusted source, so it's signed. And also the firmware has to be encrypted to prevent like, because most companies they want to prevent like hobbyists like me from like reverse engineering it. So unfortunately, Hyundai pretty much like screwed up the entire thing. So first off, the firmware was signed with RSA, which is okay by itself, just that they used a sample key. Like, it's the same thing as like forgetting to change your default password. Yeah. They also, the firmware update comes in an encrypted zip file, but the thing is that the algorithm they use to encrypt the thing is so old that it has a very well-known plain text attack. In other words, if like the attacker knows the file contents of one file inside the zip, they can get the zip password and unzip the entire thing. And inside the zip, there is a system image, and the system image is also encrypted with AES-CBC, which is fine by itself, just that they did the key they used to encrypt it was accidentally released in one of Hyundai's open source project. So everything is online. Yeah. So of course I don't know what went behind this, but I would think that I guess the developers who did this didn't know the security implications of what they were doing. Like, why do they have to sign it? Why did they have to encrypt it? And because of that, right, the parameters associated with implementing such a thing, for instance, like how are you supposed to deal with the public key? How are you supposed to deal with the private key? All these are things that the developer doesn't really know about. Which leads me to something that I call like the bad API problem. So the current state is that developers are not aware of what cryptographic operations they are supposed to do. For instance, like if you have something that you need to do, are you supposed to sign it? Are you supposed to encrypt it? Or are you supposed to like do something else? And also, even if developers know what cryptographic operations to do, it's not a trivial question to know exactly how to do it. So and this is kind of the fault of like bad APIs. So I'm going to give an example of an API that is like quite widely used last time, at least in a few years ago. So there's this set of standards called Jules. It's basically a set of standards to sign and encrypt JSON. And it supports two modes lah. So you can sign and you can encrypt. So an example of the Jules standard being used is in JWT web tokens. So in this scenario, right, you are signing stuff. So you have some data, which is the purple part, and this data is not encrypted. But instead, you append a bunch of bytes, which is the blue part, that the server can use to verify that the data has not been tampered. The interesting thing about JWT tokens, right, is that there is the red color part, which decrypts into like something they call the header, which includes a field called the alg field, the algorithm field. And the algorithm field specifies what the server has to use in order to verify the signature. But the interesting thing is that, right, it's not encrypted. Like that. So the attacker can basically modify the algorithm field. And also remember how the signature is supposed to detect whether the message has been tampered with. The thing is that, right, in order for the server to verify the signature, it needs to know what algorithm it uses, which means it needs to read a header. So the alg header, right, is kind of immune to the signature check. And this leads to the first problem lah. The algorithm field can be tampered with before the server verifies the integrity of the token. And so the possible values that alg can have, right, is symmetric encryption, symmetric signing, asymmetric signing, and a non-value for some reason. I don't know why the non-value is there, okay? Like, yeah, basically the non-value, right, is exactly what you expect. The server will just ignore the signature. And so if the attacker were to just set the alg to none, the server wouldn't verify the signature and just bypass the check. So you would think like, okay, if you are implementing GWT tokens, right, I'll just ignore the alg value. I just assume that the alg value is RSA, RS256, and ignore the header. Unfortunately, right, according to the standards, right, the server must process the alg header, which means that if you were to ignore it, right, you are technically breaking the standard. So as a developer, right, who implements a standard, this kind of thing is like shooting yourself in the foot. And also, second problem is that so this is the API for signing stuff. And the second problem is how the key is, the way the API presents the key. So the thing is that, right, the way each key, right, is not tagged to the algorithm, which means, right, you can use the same key for HS256, which is symmetric, and RS256, which is asymmetric. You can use the same key for both, which is a bad idea. In fact, right, the standards, right, specifically design the key format to allow that kind of reuse. But if you ask any like cryptographer, right, that is actually generally a very, very bad idea because it breaks certain assumptions that the primitives are designed for. Then the third problem is that, so this is if you want to encrypt anything with the Jules standards, right, a developer must choose two algorithms. And okay, I won't go through exactly why certain choices are insecure because of lack of time. But basically, the red color ones are insecure. So if you are a developer trying to implement this properly, like, yeah, you have to like pretty much answer like 2 MCQ questions in order to implement it properly. And like, it's not reasonable for a developer to like know the details and the research up to then in order to make a proper choice. So basically, Jules has an insecure standard, and it's quite opaque in terms of like what it does, like what does signing mean, what does encrypt mean, because the documentation is like quite bad, or at least like the official documentation is quite bad. And also like it makes the developer have way too many choices. It makes the developer like choose what primitives they want to use, and so the API basically leaves too much room for error. So the thing is that developers, right, when they try to implement cryptography with like this kind of API, right, they end up going very deep rabbit holes in order to implement it properly. So the solution is obviously to make better cryptographic libraries. So basically, cryptographic libraries should be proper abstractions of whatever security they are claiming to provide. So in other words, like cryptographic libraries should be easy to use, hard to misuse, and secure by default. So one such very well-designed library is DeepSodium. So this is how the API looks like if you want to hash passwords. So basically, it generates the sort for you. It doesn't leave the sort generation for you. And if you look at the parameters that the developer has control over, there are parameters that are actually relevant to the developer. For instance, like how much machine resources do you want to allocate to password hashing. And also, the developer never touches the primitives. They can use the API securely without even knowing what hash is behind. Also, right, the Libsodium documentation is very good. It provides us a few constructs and it gives very clear documentation about what that construct does. So if you're a developer that's trying to look for like different constructs to see what is best for their application, the documentation pretty much tells you everything. And also, Libsodium sometimes gives you multiple choices. And when there's multiple choices, right, the documentation, Libsodium ensures that pretty much all the choices are secure. There's no way to fuck it up. Also, right, for each choice, right, there will be limitations and stuff, and the documentation gives information about each limitation that is actually relevant to the developer. So the developer doesn't have to like pass through like research paper and stuff to see like exactly what they're dealing with. So yeah, so basically Libsodium is part of the success of Libsodium because it's like very easy to use, very hard to misuse. It has amazing documentation, and it's always secure. Yeah, so 30 minutes, yeah, that's the end of my talk. Any questions?
All right, once again, let's give it to Jules. Thank you so much for the amazing session. It was very technical. I'm sure we all agree that, right? All right, so we have about 15 minutes for Q&A. So anyone has any burning questions? Okay, once again, there's two ways of asking questions. Right, this is a cozy room. You can raise your hand and we will pass you a mic. In case you prefer to do it online, we also have another way to do it. So what you do is you go to Discord and you can go to the live thread, right? We actually have one for this talk here. There'll be a link that will take you to a online platform for you to just ask your questions, right? That will be on Slido. I'm just going to monitor this and I'll read out the questions. So two ways of asking questions. Okay, anyone wants to raise your hand and ask any questions for Jules? Don't be shy, don't be shy. Okay, I'm looking at this online platform. I don't see any questions come. Okay, I know why. My network has gone down. That's why I don't see it. Maybe I can pass it to Patricia to read the question.
Hi, a question from Chunket. Chunket, you raised your hand so you know where you are. Yeah, okay. He asked, doesn't bad API problem mean I should roll my own crypto? Example, something that doesn't care about algorithm none.
Yeah, okay, so the idea is to not roll your own crypto because the API allows it, but to find a better library. Like for instance, like the Jules standard, right? There's actually a new standard called Paseto, like Paseto, that is like way better design and like guarantees the same thing. Yeah.
Does that answer the question? Chunkit, right? Kind of. Do you want to elaborate on that?
Of course, it's fancy that, there's this old problem and then there's a better library now. But let's say at this point in time, that's all you got. And then somebody gave a talk and tell me not to roll my own crypto. And then I see there's only this library which has an ALG none. What am I supposed to do? Right? So the next step is roll my own crypto, right? So of course right now, no, now you can use this other one. But at this point in time, let's say that there isn't.
Yeah.
Because of this, so
Yeah,
what's the
so
answer?
the new cryptographic. Okay, so first off, right, again, I'm not like a professional cryptographer. So I'm actually more like specialized in academic crypto rather than practical crypto. But if you see like the new cryptographic libraries, right, they do consider backwards compatibility. So for instance, like Paseto has like version 1 and version 2. One is like version 1 is compatible with like Jules, I think, if I remember correctly. Yeah. But generally is to try your best not to implement any crypto actually. Yeah. Yeah, so sorry, I'm not a professional software developer as well, so I don't really understand like the considerations at hand.
Not so much a question, just to sort of to strengthen your answer. I'd offer a general heuristic. If you go to use a crypto system, you must not implement it. There are no exceptions anywhere on earth. The only people who invent crypto systems are people who invent good ones, are doing so under situations of extremely close supervision, and they do not use their own systems. Right? There is a total separation between the the devisers and implementers of secure crypto systems, and the users. If you are using a crypto system, you must not invent one. If you think you must, then you haven't done your research. That's really the only, it's that stark. You are going to get it wrong. Stuff like the side channel attacks for Struckump are the easy case. There are another 200 or 300 cases of side channel attacks that you need to understand. If you are someone whose job it is to implement, to use a crypto system, you do not have the time or the expertise to even know what the side channel attacks are, let alone prove that you haven't made code that's vulnerable to them. So that it's a total separation. If you're a developer whose job it is to implement and use something that uses crypto, you categorically are not qualified to implement. It's that stark, I would suggest.
Thanks, Roland. Yes, Zui.
So I have a question then. Given that all these exploits and attacks have been, they're discovered as and when someone picks it up or picks them up, and developers are unaware of all these issues because it's not in their job scope. So they go around, they pick libraries, they use it, they implement them, they roll out the systems. So based on this process, am I right to assume that there are actually a lot of vulnerabilities out there floating around?
I mean, yeah, of course. Yeah. Like imagine like if like some protocol like maybe SSL has like suddenly a vulnerability, they'll probably ask you to like update everything, but how many people update their systems? So there's always like this kind of stuff that's happening.
Yeah, it's always a cat and mouse game, right, out there. And that's why we all have jobs. I know it. Just kidding, by the way. Don't quote me on that. Oh God, oh my God. I'm not advocating anything. But okay, anyway, we have a question online as well, just to hopefully move the thread on. How do we recommend newbies to learn more about cryptography? Like, are there any books or any recommended like articles you can share?
Okay, it depends on like what part of cryptography you want. I can probably only point you to good resources if you want to get into academic cryptography, which is like CryptoHacks is a pretty good place to like start on academic cryptography. But if you want to do practical, right? Yeah, I'm not very sure. I don't have good resources. It's mostly like I mostly get it from like experience with like just I happen to touch it kind of thing. Yeah.
Yeah, if anyone wants to share, I know there's a lot of like security experts here. I see a lot of people nodding their head just now when people were talking, so I know you guys are here. If anyone want to share, just feel free to share that. It's an open forum. Anyone? Yes, come.
I just wanted to, because I was quite curious to see that just now you were talking about CVC, like, so I was just quite curious how the attacker can just splice blocks in or remove blocks?
Okay, so remove blocks is very simple. Just remove like 32 bytes of the ciphertext. If you want to combine, right, you need to add the IV of the second. Okay, so you have two ciphertexts, right, and you want to combine them together. You take the first ciphertext, you take the IV of the second ciphertext, put it here, and then you take the second ciphertext and just put it like that, and then you have concatenated the two ciphertext with a random block in the middle.
Any like MAC hash checks check for that, or
yeah, so CVC, right? Okay, there are some block ciphering modes that do have some form of checks, but CVC doesn't have that kind of checks, which is why like one reason why you shouldn't use CVC. Yeah.
Okay, sorry, one last question. Because JWT is quite frequently used in like ID tokens or access tokens, so you just said that basically I can just alter the algorithm that it checks for, so it doesn't even check for message integrity. So
okay, so the standards itself is insecure, but implementations of the standard itself have taken the liberty to interpret the standards in a very weird way in order to prevent that kind of thing happening. Yeah, but you still need to keep that in mind, lah.
alright, thank you so much.
Right, we have about 7 more minutes to go. We have all the security experts in the room, and feel free to take this opportunity.
Hi. So one question I have is, so right now, like, there's a lot of post-quantum cryptography implementations coming out. So in like cases where like new standards are like just being implemented in their libraries, like where it's not exactly battle tested and there are no not many other alternatives as well, where you're like kind of forced to pick between the choices that you have. What tips do you have to ensure that you're picking the right one?
So generally, like algorithms before they enter a standard, right, is go through like several rounds of reviews by like experts across the world. So for instance, I think there's like recently a competition that, not really a competition, but sort of like a competition between different like post-quantum protocols. And you might have heard of SIDH. SIDH was one of the finalists that was recently like completely broken. Yeah, so the idea is that it goes through several rounds of reviews before it even enters a standard. So the primitives itself, I don't think there is like much concern, though occasionally certain things gets discovered about the primitives after it enters a standard. But generally that's not, as a developer, right, that is quite a rare concern.
Any other questions? 5 minutes. We have probably time for one or two more. Let me just check online. I think there's some questions online. I just saw it coming up. All right, so there's a question that says, all right, for anonymous, whoever you may be out there, how do you usually know the encryption method of an API? Say, for example, right, we have Hyundai's firmware update as an example. Do we check their open blocks, documentations, or SDKs, or like check out the analysis of the TCP packages directly?
Sorry, can you repeat the question?
Yeah, so the question is, how do you usually know the encryption method of an API? If I may just summarize that. Like, do you check on their SDKs? Do they share it? Or do you actually go and analyze like all the packets that comes through?
I mean, there's no one solution for it. If it's open source, there's probably documentation, you can read the code. Yeah. But for like proprietary software, sometimes they even like roll their own crypto actually, like Hyundai. Okay, not Hyundai didn't really roll their own crypto, but they just implemented it wrongly. Yeah, and for the Hyundai example, right, all the research was actually done by somebody else. They actually like took the firmware and did all the research by themselves. So you sometimes do need to dig into the code if it's proprietary. Yeah.